In the last lecture, we were discussing the properties of fluids. In particular, we discussed the streamline flow and the turbulent motion of the fluid. We also discussed the viscous drag that an object feels when it moves through a fluid. Today, in this lecture, we continue with fluid properties, and we shall discuss two very important topics, Bernoulli theorem and Torricelli law. So, we start with this discussion. The fluid is going through a tube of cross section A. Then how much fluid goes out or enters in this tube per second. So, to do this, we choose a length equal to the speed of the fluid, length v. So, that the volume of this element is A times v, and the mass of fluid in this element is rho times A times v, rho, A and v. And in 1 second, since the velocity is v, in 1 second all this matter, all this fluid will come out. So, every second the fluid that comes out is rho A v. Now, suppose we have a variable cross section A 1 here and cross section A 2 here. The fluid entering per second in this rho A 1 v 1 and going out through this cross section is rho A 2 v 2, and rho is common. Therefore, A 1 v 1 is equal to A 2 v 2. So, why is it so? Because on the way there is no point where the fluid accumulates. Whatever enters goes out. Therefore, this is known as the equation of continuity of mass. Rho A 1 v 1 is equal to rho A 2 v 2, rho being common, A 1 v 1 equal to A 2 v 2. Now, along with this mass continuity, we also need an equation which tells us about energy continuity or energy conservation. So, for this purpose, we make these assumptions that the flow is streamline. You would recall what a streamline flow is. So, we assume that the flow is streamline. We also assume that fluid has negligible viscosity, what is known as inviscid fluid. Viscosity is very small and fluid is incompressible. We make these three assumptions and then we take this streamline flow. Let me explain this diagram. Here is a cross section A 1 and the cross section here is A 2. The pressure which pushes the fluid in is P 1, the speed is V 1, and from a standard or reference line, the height of this fluid element is H 1. Here these quantities are A 2, P 2, V 2, H 2. This fluid is moving, and after some time this element finds itself here, and then let us see what happens. This element finds itself here. Since the volume remains constant, therefore, A 1 L 1, A is the cross section here, A 1 L 1 is equal to A 2 L 2, because A 2 is the cross section here. This volume is equal to this, and this is V. Now, the pressure difference is P 2 minus P 1. Therefore, the work done in moving this volume V would be P 2 minus P 1 times V. The work done is P 2 minus P 1 times V, but per unit volume the work done is P 2 minus P 1. The gain in kinetic energy, you see there is the tube narrows down and therefore, the velocity increases, and therefore, the gain in kinetic energy per unit volume is half rho V 2 square minus V 1 squared, and the gain per unit volume in potential energy is rho g times H 2 minus H 1. So, if we equate the gain in energy with the work done in pushing the fluid through the tube, we get this equation P 1 by rho plus half V 1 squared plus G H 1 is P 2 by rho half V 2 squared plus G H 2, means that this quantity P plus half V squared plus G H remains constant along a streamline. Now, this is all energy, half V squared G H and per unit volume, this is all energy. So, this is the equation of energy conservation as the fluid moves along the streamlines. Usually, there is not much change in potential energy, not much change in height. Therefore, the last term G H can be dropped, and then we have P plus half V squared plus G H remains constant along a streamline, and as I said, since there is not much change in potential energy, therefore, G H can be dropped, and we have P plus half V squared constant along a streamline. That means what? That if V increases, P has to decrease, or if V decreases, P has to increase. So, along a streamline, as the fluid moves, if velocity becomes very large, pressure becomes very small, or vice versa. Let us see what is the effect of this. This theorem is called Bernoulli's theorem, that P plus half V squared plus G H remains constant along a streamline is known as Bernoulli's theorem, and let us see what the effect of this is. Imagine a house. Suppose very high velocity wind is flowing along the roof of this house. What happens? The pressure on the outside of the house decreases. Why? Because high speed wind is moving. So, the pressure here is less, the pressure inside is high. Therefore, sometimes the pressure inside and pressure outside, the difference is so much that a whole roof can be blown away. This happens especially in wind storms, high velocity wind storms. I shall show you two photographs. This damage caused becomes very severe during cyclones and tornadoes when very high velocity wind flow. Please notice especially how the roofs have been blown away. The high speed wind is accompanied by a very low pressure, and the pressure from inside blows away the roof. This can cause lot of damage. Here I show you illustrate the Bernoulli's theorem. The fluid is moving, here the speed is high, but the pressure is low. Here the speed is low, but the pressure is high. So, wherever speed increases, the pressure decreases, wherever speed decreases, pressure increases. That is the content of Bernoulli's theorem. Another application of this Bernoulli's theorem is in the lifting of airfoil. Airfoil, I told you in the last lecture, is a specially shaped object, and the streamlines go as shown here, some over and some under this. Speed is high in this region, in the upper region above this airfoil. Then what happens? If the speed is high, the pressure becomes low, and the high pressure from below pushes the airfoil up. There is an upward lift, and this is what we make use of in aeroplanes. Here is a drawing of an aeroplane, may not be very impressive, but this is an aeroplane, and you can see what is happening. There is a high speed wind and low pressure on the upper side, and low speed and high pressure in the lower side, and the high pressure from the lower side pushes this plane up. That is how the planes fly in simple terms. There are quite a few classroom activities to illustrate Bernoulli's theorem. A few are given in class 7 science book of NCERT. In addition, we give two more examples here, two more activities here. Make a paper tent as shown. I mean, you take a piece of paper and make it as a tent and put it on a flat surface, and you below the tent, you blow in this space below the tent. What happens? As you blow, the high speed wind goes through and the pressure decreases, and the pressure outside makes it collapse. So, this tent will collapse. Take another interesting activity. Take a shallow cup and put a small ping pong ball in that X stand or a shallow cup, and place it on a table, let us say, and you blow over the cup, and you would see that the ball gets lifted and floats in air, defying gravity. It does not go back, it floats in the air. If you keep on blowing, it floats in air. What is happening? when you are blowing over it, the pressure there gets reduced and the high pressure from below lifts the ball and ball floats in the air. So, these are two very interesting activities. You can find many more in books and on the internet if you search for these activities. We now take another important theorem or law called Torricelli's law. You see, the spellings are Torricelli. This person was an Italian and therefore, the pronunciation is Torricelli law. And what is this law? This law states that the velocity of a flux of a fluid, what is the velocity of a flux? The velocity with which it comes out through a hole at depth h from the top surface is given by this. See what we have done here, we have taken a vessel. In this vessel there is a fluid, water in this case, at constant height. You see water comes here and flows out here. So, the height remains constant and there is a small hole on this side. Because of the pressure of fluid, the fluid moves out of this and this is the trajectory of the fluid, and the velocity with which it comes out, called velocity of a flux, is root of 2 g h. And you would recall, it is as if a body is fallen freely through a height h. It has gained velocity v after having fallen freely through height h. In this case, this is the velocity of a flux, the velocity with which the fluid comes out. So, very interesting phenomenon we see. Suppose again we take that vessel and we make 3 holes. The first is at depth h by 4, the second is at depth h by 2, the third is at depth 3 h by 4. We make 3 holes and let the water come out. You must have done this activity in your classroom in class 8 or 9 or maybe 10. I have taken this up because in most textbooks this figure is drawn wrongly. So, I am offering an explanation of Torricelli law. So, let us calculate what the distance covered by a stream coming out of say this hole or this hole or this hole. What is the horizontal distance that the fluid travels? Remember that we are considering the level of the bottom of this vessel at that level. Remember, this is at a depth of h by 4, this is at a depth of h by 4 plus h by 4, that is h by 2, this is at a depth h by 4 plus h by 4 plus h by 4, that is 3 h by 4. So, we have 3 holes. Let us label them 1, 2 and 3. 1 at a depth of h by 4, 2 at a depth of h by 2, 3 at a depth of 3 h by 4. Let us calculate now. The velocity of a flux from the first hole V 1 is 2 g into h by 4. H by 4 is the depth, you remember. Let me show you again. H by 4 is the depth, which is g h by 2. And when it comes out, this has to fall a distance 3 h by 4. This fluid has to fall, and we must find out the time that it takes for falling this and then multiply by the velocity of a flux to find the horizontal distance by which it has travelled. That is the scheme. So, the time taken for this element of water just coming out to reach the ground level after covering a distance 3 h by 4 will be T 1, which will be equal to 2 g into 3 h by 4 square root. You recall your equations that distance covered is equal to half a t squared if the initial velocity is 0. So, from this we get 2 g into 3 h by 4. So, it is 3 g h by 2 square root of that. In this time, the horizontal distance covered by the stream will be what? Will be S 1, which would be equal to V 1 times T 1, V 1 times T 1, and you can multiply these two and you will see it is root of 3 by 2 into g h. Similar calculation we carry out for the other 2 holes, hole 2, hole 3. Similar, we get V 2 as root of g h, T 2 as the root of g h, S 2 is V 2 T 2, which is g h, S1, S2, S3 are these distances, the horizontal distances. These are S1, S2, S3. So, S1 we have just calculated. Similarly, we can calculate S2 and S3, and we get S2 is equal to GH, S3 is equal to root 3 by 2 into GH. And you can now see that GH is the largest distance. This is root 3 is 1.73 divided by 2 is some 0.86 or something like that, and this is GH. So, that is why I have shown that the middle stream goes the highest distance horizontally, and the first and the third they travel horizontally the same distance. You can see that it is root 3 by 2 GH, root 3 by 2 GH. Clearly, the stream coming out of hole 2 travels farthest in the horizontal direction. Streams from hole 1 and 3 travel the same horizontal distance as we have shown above. I have gone to this length to explain to you this diagram, because many textbooks get it wrong. You see, the lowest stream is shown going through the largest distance, which as we have calculated is not true. If the vessel is placed at a certain height, say on a stool or even higher, then it is correct to show the lowest stream going the largest distance, because the pressure is highest. If you are talking of the level at which the vessel is placed, say vessel is placed on this tabletop, and you are considering here where the streams strike, then the second one goes the highest distance. You would have realized that the situation is similar to that of a projectile, which has maximum range when it is projected at an angle of 45 degrees. In the next lecture, we have done with the fluid properties. In the next lecture, we shall start heat and thermodynamics, and we shall start with heat and temperature. We shall see what heat is, what temperature is, how temperature can be assigned to a substance, to an object, and how it is measured, and things like that. That is in the next lecture.